Hello students, welcome to eStudies. Today we are going to start the chapter 9 of standard 12 physics. The name of the chapter is ray optics and optical instruments. Friends, this is the first part of the video for the whole chapter. Friends, have a look this first slide for the introduction of this chapter. This is the electromagnetic spectrum. Friends, God has given us enormous capacity. However, God has put some limitations as well. When you look at this spectrum, you have radio waves, television waves, microwaves, radar waves, infrared waves, ultraviolet, X-rays, and gamma waves. So these are the waves, the electromagnetic waves we are using for various instruments and various equipments. However, the visible light we can only see is between 700 nanometer to 400 nanometer, and that includes all 7 colors. You may know the speed of light is 2.9979245 times 10 raised to 8 meter per second, which is 2,99,792 kilometer per second. So in most cases we use it rounded by, so which is 3 into 10 raised to 8 meter per second. That's the speed of light, and this is in vacuum though. And guys, remember, the electromagnetic waves are not the mechanical waves. I mean, the light waves are not the mechanical waves, and therefore it can travel in vacuum, whereas the mechanical waves need a medium to travel. You guys would wonder that if the light is an electromagnetic wave, then how come it can travel in straight line? And I think that question makes sense as well. However, that we must know that light actually appears to travel in straight line due to the very small wavelength. And as a matter of fact, what happens that any diffraction of the waves is so least that it causes light to travel almost in straight line. So the light wave travels from one point to another, and between the 2 points it travels into straight line. So if you join the path of the light wave, we can say that path a ray of light. And when you bundle such waves, then it is called a beam of light. So friends, in this chapter we are going to learn reflection of light, refraction of light, dispersion of light, image formation on plane and spherical reflection, and refracting surface. Construction and working of optical instruments, including human eyes. So let's start with laws of reflection of light. Note students, here mainly in this chapter they have discussed about the reflection of light by a spherical mirror. The first law indicates that the angle of incidence is equal to the angle of reflection. So the angle between reflected ray and the normal is the same as angle between the incident ray and the normal. The second law indicates that the incident ray, reflected ray, and the normal to the reflecting surface at a point of incident lie on the same plane. So they are all on the same plane. Students, these two laws you have studied in your earlier classes, mainly in standard 10. You have learned this. And you may know that these laws are valid for curved surface and the plane surface both. Students, you may be aware that a tangent is a straight line just touching a curved surface at a point which do not cross that particular curved surface or the circle. Here it has been described that the tangent to the point of incidence. So students, when you think about a normal to any curved surface, that you got to consider that the normal to the tangent of that particular surface. at the point of incidence. As we can imagine that the spherical mirror is the part of a big sphere, and the center of that particular sphere can be considered as C, and from that point to the P, the pole of the sphere is a radius, and hence the normal is taken as the line along the radius of that particular sphere, and that is at the point of incidence. Hope this idea of tangent to the point of incidence makes sense to you. In the next slide, we have a geometric center. For the spherical mirrors, we have pole P is a geometric center. Also remember, students, that the line joining the center of the curvature and the pole P of the curvature is called the principal axis. Whereas in the case of lenses, the principal axis is the line joining from its optical center to the principal focus. That's the principal axis. The geometric center is the optical center, which is the center of that particular lens as shown in this slide. Next, we got to understand the sign convention, which is important to understand the formula for the reflection by spherical mirrors and refraction by spherical lenses. So students, in your book in 12th, we got to follow the Cartesian sign convention. According to the Cartesian sign convention, all the distances must be measured from the pole of the mirror or the optical center of the lenses. The distances against the incident light is taken as negative. The distances measured towards the direction of incident ray to be measured as a positive. The height of the image formed downwards is taken as negative, and the height of the object measured upward is taken as positive. In the next slide, we have got the focal length of spherical mirrors. So students, here we have the first figure of concave mirror, and we assume that the beam of light comes parallel to the principal axis, or it has got a very small angle with the parallel axis and it incident on the surface of the mirror. Once they incident on the surface of the mirror, they get reflected and converge at a point F, which is a principal focus on principal axis. Secondly, in the case of a convex mirror, same thing, parallel beam of light incident on the surface of the mirror, and because it is a convex mirror, that they appear to diverge from a point F on its principal axis, and we get the virtual image. Students, remember here that in the case of concave mirror, we are getting a real image because the rays actually reflect and converge at a point F. Now looking at the third figure, students, that when the rays are incident and making some angle with the principal axis, after reflection they would converge at a point in a plane through F normal to the principal axis, and the gray area here highlighted is called the focal plane. Students, as we know that the focal length F is the distance between pole P and the principal focus F. Now let's understand that how F, which is a focal length, is equal to the radius divided by 2, which means that the focal length is the half of the radius. Here we have been given two figures. The first one is for the concave and the second one is for the convex mirror. So in order to understand, let C is equal to the center of the curvature. CM is perpendicular to mirror M. Remember students, we have got this curved surface, and we are drawing a line CM which is at right angle at that particular point M. Theta is the angle of incident. Now we can see here that CM is the normal, and the angle of incident theta is the same as angle of reflection to the normal. MD is perpendicular to principal axis. Now students, look at angle MCP. Angle MCP is theta, and angle MFP, which is double the theta, therefore it is 2 theta. Here students, as you know that for an acute angle in a right angle triangle, the ratio of the opposite side to the adjacent side is tan theta. We can say here that tan theta is equal to MD upon CD, and tan 2 theta is equal to MD upon FD. We'll give this equation number 1. So students, as we know that if theta is small, then point D would be very close to point P. If the theta is bigger, then point D would be bit far from point P. Therefore, we can say here that tan theta is almost equal to theta, and tan 2 theta is almost equal to 2 theta. Now, we can say that the ratio of MD and FD is twice the ratio of MD and CD, or FD is equal to CD divided by 2. Now students, as we know that the distance between point P and point F is the focal length, and here we have got theta is very small. So because theta is very small, we can say that FD, the distance between point F and point D, is equal to the F, which is focal length, and CD is equal to R, which is radius. Therefore, we can say that the focal length is equal to half of the radius, so which means F is equal to R by 2. Moving to the next slide, we have the mirror equation. Let's try to understand. So students, what is the image? In a simple term, if we say that the rays emanating from a point, and after reflection or refraction they meet at the another point, that point is called image of the first point. Hope this makes sense to you. Now I am reading out the definition given here. An image is a point-to-point correspondence with the object established through reflection or refraction. As we know that from an object there would be millions of rays emanating at a time, but just for the convenience we are taking, or we are choosing, any 2 rays out of the 4 rays given here, just to understand the principle, and in order to trace their path and find their point of intersection and thus obtain the image. The first one here is the ray from the point which is parallel to the principal axis. So when there is a ray parallel to the principal axis, it gets reflected from the surface of the mirror and it passes through the point F, which is the principal focus on the principal axis. The next one is the ray passing through the center of the concave mirror appear to passing through for the convex mirror, and what happens that it gets reflected to the same path. In the third one, when the ray passing through the principal focus of the concave mirror or appear to pass through the convex mirror, that ray after reflection travels parallel to the principal axis. In the fourth one, when the ray incident at any angle at pole, it follows the laws of reflection. So that means that the angle of incident and the angle of reflection would remain same to the normal. Students, in the next slide we have got a diagram, and we have got three rays coming from point A. The first one is coming parallel to the principal axis and gets reflected at M, and the second ray is coming from A and incident on P and gets reflected, and then the third ray, which is coming from A and passing through C and gets reflected at the point N. Note students, here they have only shown three rays, but as you know, there will be many millions of rays would be emanating from an object. So this is just only for understanding the principle behind it. However, if all the rays emanating from point A and gets reflected on the mirror surface and passes through the point A dash, and then that will be the image of A over there, and it will be applicable to all the points of the object AB, starting from A to A dash and then up to B dash. We can have the whole image created as a result of the reflection of all the rays emanating from that particular points of the object. Now let's try to understand that how mirror equation is derived and the relation between the object distance u, image distance v, and the focal length f. We have two right angle triangles here. So look at the first one, A dash B dash F. The area I have filled with green color. Then look at the another triangle MPF, which is another green area highlighted, and these two triangles are similar. Now the ratio of B dash A dash to BA is equal to the ratio of B dash F to FP. Here note students that PM is equal to AB. Students, I have highlighted angle APB with the green color and the angle A dash P B dash with red color, and they are equal as they are theta, and they are the angle of incident and angle of reflection. Since we have got angle APB is equal to angle A dash P B dash, the right angle triangle A dash B dash P and ABP are also similar, which I have highlighted with gray and green color respectively in this slide. As a result, the ratio of B dash A dash to BA is equal to the ratio of B dash P to BP. We'll give this equation number 2. Now when you compare these two equations, the equation 1 and the equation 2, we get B dash F upon FP is equal to B dash P minus FP divided by FP is equal to B dash P upon BP. Students, this equation shows us the relation of the magnitude of distances. Now let's apply the sign convention. As we have discussed earlier that in Cartesian sign, the rays traveling from object to the mirror are to be taken as positive, and we have to travel in the opposite direction of the incident ray in order to reach to the object AB, image A dash B dash, and the focus F from the pole P. And therefore all three will have the negative signs. So B dash P is equal to negative V, FP is equal to negative F, and BP is equal to negative U. Now if we use equation 3 here, that negative v plus f divided by negative f is equal to negative v upon negative u, or v minus f upon f is equal to v upon u, we get. And therefore v upon f is equal to 1 plus v upon u. Now students, if we divide both sides by v, we get 1 upon f is equal to 1 upon v plus 1 upon u, and this is the relation is known as the mirror equation. As you would know that the size of the image would be relative to the size of the object, which is also important, and we need to consider it. So if I want to find out the ratio of the object's height and the height of the image, I would call it linear magnification. So I will denote it as m. So m is equal to h dash divided by h, and that will give me the ratio of the heights. Note here h dash is equal to height of the image, and h is equal to the height of the object. Remember students, you got to take height either negative or positive, and you got to follow the rules of the Cartesian sign convention. So students, in triangles a dash b dash p and abp, we have the ratio of b dash a dash to ba is equal to the ratio of b dash p to bp. So the ratio of negative h dash to h is equal to the ratio of negative v to negative u. So the linear magnification m is equal to h dash upon h is equal to negative v upon u. So students, we have derived the mirror equation and the magnification formula, which we'll use for the sums we will do in the next part. Now here we are concluding the first part of this chapter, and please be with us, and thank you for watching.